Welcome back. In the last episode, we explored how temperature shapes performance, turbulence, and flight planning. Now we're diving into a critical factor often overlooked: humidity. Moisture in the air plays a massive role in visibility, cloud formation, and aircraft performance. Let's break it down. Humidity is the amount of water vapor in the air. It's invisible, but it affects nearly everything in aviation, from weather development to engine efficiency. There are different ways to measure it, but the most important are absolute humidity, specific humidity, and relative humidity. Absolute humidity is the total mass of water vapor in a given volume of air. Specific humidity is the mass of water vapor relative to the mass of air. But pilots mostly care about relative humidity, the percentage of moisture in the air compared to how much it can hold at a given temperature. Warm air can hold more water vapor than cold air. That's why relative humidity increases as air cools. When the temperature and dew point get close, the air is nearly saturated. This leads to cloud formation, fog, and even precipitation. The dew point is the temperature at which air becomes fully saturated, 100% humidity. When the temperature drops to the dew point, water vapor condenses into liquid. This is how clouds, fog, and dew form. The spread between the temperature and dew point is a great predictor for cloud bases. A small spread, say, 1 to 3 degrees Celsius, means clouds are close to the surface. A larger spread means higher cloud bases or clearer skies. There's even a handy rule of thumb: to estimate the cloud base in feet AGL, subtract the dew point from the temperature, in Celsius, multiply by 400. For example, if it's 20 degrees Celsius with a dew point of 15 degrees Celsius, expect cloud bases around 2,000 feet. Humidity also affects visibility. High humidity makes it easier for water droplets to form in the air, leading to haze, mist, or fog. Even when skies look clear, high humidity can reduce visibility to just a few kilometers. There are 3 types of fog common in aviation. Radiation fog forms on clear nights with light winds and rapid cooling. Advection fog forms when warm moist air moves over a cold surface. Upslope fog occurs when moist air is forced up terrain and cools to saturation. All types of fog can severely reduce visibility and even close airports. It's one of the most frequent causes of delays and diversions, especially in coastal or mountainous areas. Humidity also plays a role in density altitude. Water vapor is lighter than oxygen and nitrogen, so humid air is less dense than dry air. That means fewer air molecules, less lift, and reduced engine performance, just like flying at a higher altitude. On hot, humid days, your aircraft will require more runway, climb slower, and may not reach expected cruise speeds. That's why performance charts factor in temperature and humidity when calculating takeoff and climb capabilities. Let's take a practical case. It's 30 degrees Celsius, with 80% humidity. Even if you're at sea level, your aircraft behaves like it's at 2,000 to 3,000 feet elevation. Knowing this in advance helps you plan fuel, rotation speed, and route alternates more accurately. Humidity also affects icing risk. When relative humidity is high and temperatures fall near freezing, the chance of airframe or carburetor icing increases. Moisture condenses and freezes on surfaces, adding weight and drag, and affecting lift and control. In carbureted engines, humid air increases the chance of carb ice, especially between -5 degrees Celsius and +15 degrees Celsius. Even at idle or descent power settings, moisture can freeze inside the venturi, choking airflow and reducing power. Use carb heat early and often in these conditions. Humidity influences cloud development as well. Moist air rising into cooler layers condenses more easily, creating cumulus clouds, towering CBS, or stratiform layers. If the air is dry, rising air won't form clouds, it just warms and sinks again. Let's connect this to weather briefings. METARs often report temperature and dew point. If you see a small spread, like 18/17 degrees Celsius, it's likely that fog or clouds are forming. Always pay attention to dew point trends in your destination's weather. TAFs may forecast BR4 mist, FG4 fog, or HZ4 haze. These are all related to high humidity. Fog and mist form with near saturation, while haze can appear in humid, polluted air. All reduce visibility and should be planned for in VFR or IFR ops. Humidity also plays a big role in tropical weather systems. Warm, moist air over oceans fuels the development of tropical storms and hurricanes. As moisture condenses in updrafts, latent heat is released, powering the system further. Let's summarize what we've learned so far. Humidity is invisible but essential to flight safety. High humidity leads to lower visibility, clouds, fog, and icing. It reduces air density and performance. Dew point and temperature spread help predict weather formation. Fog types and humidity levels are key for pre-flight decisions. In the next episode, we'll continue with humidity, part 2. We'll explore humidity's effect on weather systems, how to interpret moisture data on charts, and tools for managing humid conditions during flight. See you in Meteorology number 15, Humidity, part 2.